college and R1, R2 institutions, so somewhere in between. And I work with computational material science in collaboration with Kristen Person, who is the director at Materials Project at Lawrence Berkeley National Lab. All right, so I will just start my presentation. Is that okay, Nakia? All right, so I'm going to share my screen. Okay, so let's see. All right, so the talk will be on use of artificial intelligence, AI, enable computational material science to do two things, basically, surface dynamics and modeling of complex system. I'll get to the minute what they are. I want to acknowledge my student, Tyler McGilvery James, who is also part of this program. Like I said, we are both from Missouri State University, and our host is Kristen Person, and at the Materials Project as a director of Materials Project, among other things of her in her capacity. I would like to acknowledge workforce development and education and this program that allows us to being able to use this opportunity for the summer. I gotta say it's quite a blessing. I am very grateful for this opportunity. Some of this work is a continuation of the work that we've done, sponsored by DOE, NETL, and NSF from Electronics, Photonics, and Magnetic Device Program. So I would like to acknowledge that. And of course, since this is computational material science, we are very, very grateful for the NERSC giving us the allocation, both at Corey and Perlmutter. And I actually took this title here, or this logo, Connect, Collaborate, and Create, from actually from Workforce Development and Education website. And I think this is really embody sort of what this program is about. We are able to make connections. We are doing collaboration now, and we are doing, I believe, a creative work in research that are, to me, is a great privilege. So I want to thank you for all this opportunity. So let me start with the, I would give my props to my group at Missouri State. So particularly, I already showed you that Tyler is working with me for the summer. Mo is also helping us with, Mo, Aziz, and Gage, they are RA students right now doing some research at MSU. Devon and Emily just graduated, and so some of the portion that I work, actually, I would sort of include this in the presentations as a background. We have our website too, if you would like to see what we do. All right, so the outline. I would like to give a little bit about information about the research area, which I said already at the beginning, which is modeling atomic layer deposition and complex systems, two different research area. The approach that we use, the type of compositional strategy, especially for complex system, and deep learning methods that we use to develop the interatomic potentials. How we verify, and then some demonstration of application of these AI interatomic potentials. Of course, 30 minutes won't be enough to cover all of these, and I'd be more than happy to answer or communicate with anybody that would be interested in this type of work. And then I will finish with the sort of things that we want to do. We are halfway, essentially, which is related to accelerated MD simulation and integration of our data and our work into Materials Project, which is the sort of the massive database that are being hosted here at Lawrence Berkeley, and is pioneered by Christine. And I will conclude with summary. So just to give a little bit of a sort of a primer here, surface dynamics, atomic layer deposition is essentially a technique that is being used nowadays, especially nowadays, to deposit thin films from a vapor paste into a substrate. And this is done through a series of very carefully sort of designed chemical reactions that is meant to produce essentially layer by layer depositions. So sort of this is a little bit of a cartoon here showing that you use essentially two types of precursor. One is like a TMA, trimetal aluminum, which would deposit into a substrate, essentially an aluminum carrier. And through a second stage after the purge, which is the second process, we deliver the second cycle of this ALD, which is usually using water. And the water is basically carrying the oxygen. And through the ligand exchange, essentially between metal ligands with essentially hydrogen that create metal gas, you end up getting essentially inorganic layer of alumina. And this process is, repeated over and over. And because of the manner by which the preferential deposition takes place, this layer is it's called the self-terminating layer. In other words, you produce the one layer first, and then the second layer would go on top of the first layer, and so on and so forth. And this has the advantage of providing conformity, which is very, very critical, especially once you think about something that is sub-nanometer layer thickness. So this is sort of a cartoon that I took from this website, and you can see the first ALD cycle would essentially create this interaction between, in this case, would be a titanium tetrachloride with OH as already being absorbed on the surface. And then on the second stage, you can see that it would leave out basically with the essentially the organic portion of the layers as a product. So we did modification into this, and then we already published this actually as part of our collaboration with experimentalists at KU, at the University of Kansas, which is where we add essentially aluminum layer as part of the sort of a way to enhance the wetting behavior of the initial substrate. And the goal here is basically to use aluminum as a way to increase that coverage. And the reactions basically would go through essentially 4 steps. One is using aluminum substrate, and this would create sort of facilitate dense water or OH layer, hydroxylated basically aluminum 111. And then we use the same cycle, which is using TMA and OH as part of the ALD cycle. And with now one would say basically if the process is aiming at something like a very thick layers, this is not necessarily something that of great need. However, once you think about, for example, using this for superconducting Josephson junction as qubit, for example, in quantum computing, where the layer is the quality of the layer has to be extremely good, leak-free, and it's in the sub-nano layer thickness, which is essentially almost like only 4 layers thickness, it becomes a critical issue. So one of the goals that we are trying to do is really to be able to aim at perfecting essentially this Josephson junction. And our part is to understand basically the tunnel barrier formation of the alumina. This is a work or summarized work of or facility at KU by my colleague Judy Wu. So long story short, you can see that when you add this aluminum, essentially you can affect the barrier height, and that would essentially improve the quality of the tunnel barrier. So there's some of this work already published. So what's the sort of the next step? Well, it turns out actually when you model this type of ALD process, the difficulty comes with the fact that surface dynamics requires accuracy at the essentially DFT calculation level. However, the involvement of many of number of atoms that engage in the surface reaction itself would necessitate you to have a large scale of simulation. So one of the limitations with DFT, as probably some of you already know, it's a scaling problem, right? So it has essentially cube dependence. So that essentially quickly limit our ability to model beyond, typically 50, 100. If you're lucky, you can do maybe 400, 500, but not by much for as far as the duration of the time. You can only get probably a few picoseconds, maybe tens of picoseconds if you have a great allocation in supercomputer cluster. So that this is what limits our ability to do that. Now I should mention that in fairness, there are alternatives to do the simulation, which is actually done by some of my students or previous student. Devon actually just published his paper on using analytical force field potential, which is ReaxFF. But what you will find is basically a lot of this potential, this analytical potential, is essentially catered or being tailored into a very particular chemical reaction, surface chemical reactions. So you can see here, for example, some of the steps that involve, and depending on what type of ReaxFF potential that you use, you may end up getting different essentially energy barrier. Another approach is using kinetic Monte Carlo. There's a link there from my student Emily, where you use a kinetic Monte Carlo to essentially model basically the full length of the thin film depositions, but it still have quite a limitation because number one, it has to be, in general, it has to be on lattice type calculations, which basically means it's a grid-based KMC. It's not off lattice. And second, which some of you probably know with kinetic Monte Carlo, you do need to actually have an intermediate or essentially the long list of reaction rates and path defined a priori, right? In other words, you have to have those reactions well defined. And another thing also I should mention, there's some limitation as well with the masking and so on and so forth. So our goal here is really to solve using classical, but using machine learning potential. So moving on to the second complex system that that we're working on. This is a multi-phases in nickel-based superalloys. If you sort of, again, just a quick primer, superalloys is made of essentially nickel-based materials that is mixed with other elements. So commercial ones like 282 or Inconel 74H. These are things that, let's see. Ooh. Okay, I have 30 minutes, right? Am I correct, Nakia?
No.
Oh, okay.
You have 10 and 5
10
minutes per
all right.
question. Yes.
Okay. I'll make it quick. All right. So these are sort of the structure. Typically, you have a gamma prime, and then let me quickly. On the grain boundaries, you have this carbide essentially that is made up the grain boundaries of nickel based superalloy. So the approach we use, and again, I'm just going to make it very quickly here. We use 2 different codes. One is deepened, which using strictly local descriptors as part of the deep neural network. There's a new one actually developed by people at Harvard, just actually published 2 months ago. It's called Allegro. And again, I apologize, I'm not going to be able to get into so much into this, but the big difference here is in Allegro, you decompose basically the energetics of per atom energy into essentially pairwise descriptions, or also some of the pairwise descriptions, and then they use actually a tensor-based equivariant latent space for the displacement vector. So this allows them to be able to get to the accuracy and also the scaling as well. So again, this is just the training that we use, the type of training we normally use, which is a few, up to 100 atoms for training for the ALD, and for the bulk module, the bulk alloys, we use essentially different compositions. We test from the high entropy as sort of the center of the compositions, as well as the corners. We extend that basically to higher orders. And this is basically allows us to go to this commercial system. Quickly, the type of sample we use is all kinds of basically crystalline as well as melt system. So these are sort of some of the tests we did, surface dynamics, using water, TMA, which is for the LD process. We tested also the ability on the absorption process or the stability on these molecules on the aluminum surface. Sorry for different colors. We like to use different colors for different system. And then this is sort of an aggregate where you have a aluminum with multiple steps, and then you can see the absorption of water, sort of a first step of the ALD process. Going back to the super alloys, we tested obviously the validations of this potential by comparing our force, our energy, as well as virial with respect to the DFT calculations. This is actually just, again, this is part of the prior work that I've shown here, and we tested also the stability. We tested as well on the mechanical property, the propensity to work to produce partial dislocations, stacking faults along the 111 slip planes. And quickly you can see here an example of just a compression test, and where you can actually map out some of the dislocation types being produced. And of course, you will see the stress strain curve. In this case, a uniaxial, so you only have the X component having a stress system. Moving on to a larger system where you include the gamma prime and with the carbide as a multi-layers. And you can see that actually during the compressions, we'll be able to generate the dislocations, activity, and the density. And actually, this is moving on later on toward dislocation velocity calculation and so on and so forth. Which and this is another example of a large system where we have carbides as the sort of the representation of the precipitates, and the gamma, which is made of multiple component system. Currently, we're working with a 10 component system, 7 components in the gamma prime, and then essentially additional 3 as a carbide former. Last but not least, we just got this actually yesterday. We put the whole sort of ecosystem where you have a gamma prime and the precipitates as a carbides in one system, and then we apply compressions, and you can see some of these particle dislocations that is sort of permeating inside the matrix, which is the sort of the weakest sort of portion in the metallic system. With that, I'm going to show you actually what our plan to do, which is only 2 slides here, which is one is with the completion of this, we are collaborating with a lot of members as part of the materials project in sort of porting this into their massive database. Of course, with the inclusions of some of these sort of additional sort of columns of sets of data that sort of descriptors that allow people actually to quickly find some of these data easily in materials project. I should mention actually another one also is to accelerate the molecular dynamics is using either inclusion, of course, if it's a molecule system with a long-range electrostatic interactions coupled with model compressions. This is sort of an example in deepened in conjunction with something like a parallel trajectory splicing algorithm, parslice, which is included in the XALT. And our hope is actually we will be able to complete this within the 4 weeks left or 5 weeks that we have. It is just an example of, I should say, the OMP contributes that we want to be able to add into the materials project. And in summary, I just want to say that we've been able to develop this AI-based interactive potentials, both for the ALD process as well as the nickel-based superalloys. We use 2 types of methodology, deepened and Allegro. And our big hope is that we will be able to use this as a template for a future work where a lot of this data that can be used by others, so it be disseminated to the public through materials project. With that, I want to thank everybody for listening, and that is it.
Now we'll have time for a few questions. If anyone has any questions, now would be the time to ask. If there aren't any questions, we will now move on to the next presenter, which will be Richard Lombardini.
Well, I think there's a question in the chat
Oh, I'm sorry. Let me ask. Okay, the validation is actually it's a long process. So we tested it against, first of all, the ground state data. So that would be elastic constant, CIJ, thermal expansions, lattice parameters, lattice conductivity, and then we also compare our phonon dispersion curve against basically DFT calculations. So that's one. Second, we try also the dynamics part, which is the melting points. We also look at essentially stability, basically, of these phases. So we use compositional change. So if you notice that a lot of these samples are 100 atoms only, we test it. We have limitation, obviously. So we test it up to about 500,000 atoms. We test it against polycrystalline structures. So those are sort of a list that we do, actually. Of course, initially we compare the fitting, right, between the energy, stress, as well as the force, the Cartesian force for our data, as well as the training, as well as the validated. So I hope that's answered that question.
A very nice talk. I just was trying to better understand the state of your data readiness. So from the source that you create until you go to the modeling, what kind of steps do you take to have a model ready data?
Okay, so that comes where that machine learning potential generators are coming from. So you are actually using those data. Typically, it's a trajectory data, right? So it has information of force, energy, and Cartesian force, as well as virial. And these data are fed into to these codes, essentially through some essentially embedding neural network that would produce essentially a descriptors. So that in the DeepMD is strictly local, and the goal of this embedded network is so that you can generate essentially representation of the local environment as an invariant, as a scalar sort of a latent space. Okay. Now in the Allegro, they have other things also added into that, which is the equivariant latent space that being added. So there's two different methods basically being used, but the approach is essentially that. You transition through some type of essentially embedded neural network into an essentially mostly invariant descriptors that is invariant toward translation, rotation, and so on and so forth. So once you have that, then you go through the process of deep neural network, where you go through a hidden several hidden layers and so on and so forth, and then at the end you produce basically your potential energy surface.
So this step is proprietary or public?
No, I mean these are all published actually. So you can actually, there's a paper there, so you can see the type of sort of approach they use, both to generate the descriptors as well as the type of algorithm for hidden layers. Typically, this is using Adams conjugate gradient minimizations that it's well known in machine learning.
Thank you.
Any more questions? Okay, we will now move on to Richard Lombardini.
Thank you.
Richard, you're
Sorry,
muted.
I forgot to unmute myself. There we go. Okay, can everybody hear me now? All right, good. Okay, so let me just get started here. I just want to start off telling everyone where I'm coming from. I'm a professor at St. Mary's University in San Antonio, Texas, not St. Mary's College, which is just over the hills. This is a different university, and this is the oldest Catholic university in Texas, established in 1852 by the Marianists or Society of Mary. There is actually a Marianist high school in San Francisco called, I think it's called Reardon. I don't know if I pronounced that correctly. But anyways, many high schools, there are two other universities that are also of this order, Marianist order, Dayton and Chaminade. And all of the things that they espouse, anybody of any faith or lack thereof would definitely get on board with it. It's very pluralistic in that regard. And so education is a big deal at St. Mary's University. I have about 2,000 undergrad students. It even has a law school that is the only one in San Antonio area. And there's a lot of master's programs. Our department, we're actually combined with environmental science. I'm in the physics department, but the physics part is very, very small. There are 3 faculty. I'm one of them. And we usually, on average, we probably have about 20 undergraduates. We don't have any graduate students. We've had up to 30. But one of the things that we boast in our little physics department is that since 2011, we've had 27 of our alumni from our little department get doctorates. And so we were very proud of that. Mostly PhDs in physics, some PhDs in engineering, some MDs, and some DMPs, which is a relatively new doctorate, which is in medical physics. And so we are very proud of that, and therefore we're very focused on undergraduate research. And so here's the team that welcomed us with open arms. This is the microelectronics modeling team at LB&L, and our fearless leader here is Andy Nonaka here, and we have Reva, Jackie, and Sarab and Prabhat. Also, they're part of the group, and they welcomed myself and my undergraduate student here, Aaron Rodriguez, who's a junior mechanical engineering at St. Mary's University. And they've welcomed us and they've put us to work rapidly. And we've been learning a ton and enjoying it a lot. And I was curious to know where this microelectronics modeling team falls within the organization of LB&L. And I kind of outlined it here. We are basically in the computing science area which is, and then, well, as you go deeper, we're in the applied mathematics and computational research division. If you go deeper, we're in the applied mathematics department, and deeper, the Center for Computational Sciences and Engineering. This was very interesting to learn. I wanted to make sure I knew where we fell in the whole lab system here. So let's see here. So next, what is our research question? I'm trying to get this out of the way. Well, there is this code package that this group is modeling called Artemis, which stands for Adaptive Mesh Refinement Time Domain Electrodynamics Solver. As you can see in the name, it is a time domain solver. So it uses finite difference time domain methods, and basically it's for electrodynamics, and so it puts the electric and H fields on the staggered grid known as the Yi lattice. But anyways, in particular, we're looking at the research question is, can this newly developed Artemis software package be used to model the coupling of electromagnetic radiation and superconducting materials? And this is something superconducting materials is something new to me, so I got to learn something new. And just recently, the team was able to couple electromagnetic radiation and ferromagnetic materials very successfully by coupling Maxwell's equations with the Landau-Lifshitz-Gilbert equation, and did some great work with that. And now they're trying to couple it with superconducting materials, trying to couple Maxwell's equations with the London equation. And one of the things that is different with the London equation that makes superconductors different than perfect conductors is this Meissner effect, where you get this expulsion of the magnetic field. And I'll talk about that more as I go through the slides here. So the theory is actually not too bad for superconducting materials. First off, regular conductors, you can model the normal conduction electrons in regular conducting metals using Ohm's law, where here J is the current density, J sub n. I put the little n there to to designate normal. And sigma is the conductivity and E is the electric field in the material. And now when you have superconducting materials, okay, or when you have materials when you reach some sort of critical temperature, some of those electrons pair up. Electrons of opposite spin and momenta pair up, known as Cooper pairs, and they form these super electrons, and these super electrons don't feel any sort of resistance, okay? And so you have this current JS, and there's no voltage that is affiliated with that current, but the relationship here, this is known as the London equation, developed in 1935 by the London brothers, Fritz and Heinz, I believe. And they found this relationship here that you could add on that would take into account the Meissner effect. But here we have that this relationship here with the superelectron current is the derivative is related to the electric field in this way, where mu is the permeability of the material. And lambda is known as the London skim depth. And this is if you have a static field and you're at complete and you have all super electrons in your material, then lambda would be the skim depth of the superconducting material. And I'll talk a little bit more about that later. And it's also, it treats both this superconducting current and normal current basically as two parallel channels of current. So if you're in a temperature between the critical temperature and 0, you've got this mixture of normal conduction electrons and super electrons that are flowing through, and they don't interact with each other. But anyways, the idea is to couple London equations with your regular Maxwell equations. And here we see that the divergence equations are the normal Gauss's law, this curl V is the Faraday's law, this is the Ampere's next, and then we're looking mainly at linear media, and these are the constitutive relationships here. So I am not by training a material scientist, and so I had to learn about superconductors. And there is there's quite a few differences, but one difference in particular that's very interesting between a perfect conductor and a superconductor. And I fortunately had great access to some great books, and this one in particular, Superconductivity and Introduction. And I think this picture that they provided explains it so well. So first off, if you have, let's say you have two materials, one is a normal perfect conductor. I mean, that means like a conductivity that's infinite. And you have a superconducting material. Let's say that you cool them down to below the critical temperature. If you turn on a magnetic field, which is uniform, both will do the same thing. They experience by Faraday's law, if these metals experience a change in a magnetic flux, they will induce a current here that basically goes in the direction of producing a magnetic field that opposes the introducing magnetic field by Lenz's law. And this is something that I teach my undergrads. And so, yes, I was good that I saw something I recognized here. Now, with a superconductor, what happens? There's some differences between that and a regular conductor. So let's say instead of cooling the material first, let's say you have a magnetic field first, then you cool the material down to the critical temperature, and that's where you see the issue, so the differences between a perfect conductor and a superconductor. And that's in that middle right here. So in the normal conductor, you're not going to have anything because there's no change in magnetic flux of any sort. And so you're not going to have any sort of Faraday's law that's going to be coming into place. But with a superconductor, you have the Meissner effect. And what happens is there is a screening or London current that occurs, producing a magnetic field that opposes the B0 magnetic field. And then inside there is no magnetic field. So there's this expulsion of a magnetic field. This is different than what would happen in a regular conductor. And also, then if you turn the field off, the normal conductor is going to have, by Faraday's law, is going to induce a current, and you're going to have a magnetic field from that. But with the superconductor, you're not going to have anything that happens in that case. And so that on the right there shows the difference. And so regular Maxwell's equations does not provide these differences for the superconductor, and that's why you have to introduce London equations into the mix. Okay. So I got out my trusty Griffith's undergraduate E&M book and was looking at, okay, well, what are some things that we can do to look at Artemis? So recently the team put London equations into Artemis, and we wanted to see, is Artemis giving us the right physics, what we should see? Okay, so that was our task, Aaron and I, that was the task that was given to both of us. And I got out my Griffith's undergraduate book and found, all right, well, let's look at skin depth. Okay, that's the depth at which a field travels in a conducting material. It's the distance at which the amplitude will be reduced to 1/e, or 36.8% approximately. And, we tried it, we looked in my book and found here is kappa, where 1/kappa is the skin depth. This is a derived equation for it, where epsilon is the permittivity of the material, mu is the permeability, sigma is the conductivity. And so just to see if we're using the code correctly, we tried it out and on a conducting material, and this one on the right has a permittivity, has a high conductivity, has a skin depth theoretically of 5 microns, and we ran it, and lo and behold, we got that. And so we were happy. Okay, so we know how to run the code. And so then I sat down and with some just pencil and paper and see if I could work out, if you include London equations, can you get a skin depth from that? And I was able to derive this expression here, and you can see here it now has this new term lambda, which is the London skin depth in there. And one thing you can notice that if sigma is 0, and if omega is the frequency, by the way, if the frequency of the wave that's being introduced is also 0, that would omega equals 0 would correspond to like a static field case. This would basically reduce the skin depth, would reduce to lambda. And so, we tried these cases, and unfortunately we couldn't match up with Artemis at this moment. And so we're still trying to work out why that is. And usually in the case, you get a very, very small skin depth. Lambda tends to be in the nanometer scale. Okay. So another thing we looked at is reflection coefficients. Okay, so what is, when you have a wave that hits the surface of a metal, what is the percentage that is reflected and what is the percentage that is transmitted? And you can derive expressions for that. And we looked at the conductor. We wanted to make sure we were using Artemis correctly. And the red line is our experimental, black line is the theoretical. And we saw, yeah, okay, there's a match. Now, obviously, we could have fit the red even better if we use higher resolution, but we were satisfied with that. And we tried with the superconductor, and there's a certain behavior that's very interesting with superconductors, is there is a certain frequency where below the superconductor has, and this is this black line, has 100% reflection, or when the reflection coefficient is at 1. And we were trying to see that if we could get that behavior with Artemis, and so far we have not been able to. And there's multiple reasons why that could be the case. Could be we're not quite understanding the physics correctly. 2, we're not using Artemis correctly, or maybe there is a bug in Artemis. We don't know, and that's the name of the game. Aaron and I are trying to figure out what we're doing wrong, or what the code is doing wrong, or we have many questions, and so we're doing many different tests, and so it's been quite a neat problem to address. So, why the theory that we have and the simulation are matching? That's the big thing that we're trying to figure out. And hopefully we can find that out soon, because there are many applications that we can use this Artemis with the superconducting capabilities. I mean, there are lots of papers that are coupling ferromagnetic materials and superconducting materials for quantum computing architectures. And since the ferromagnetic capability, which by the microelectronics team has recently been successfully implemented, it'd be great to get the superconducting work, and we can model, this quantum computing ideas. And superconducting transmission lines are a big deal. I mean, that's, providing energy and information at very low power dissipation. Very, very important things to model. We've seen papers that talk about nonlinear behaviors with superconducting material. You can add more features than just the London equation and get even more accurate modeling of superconducting materials. And so basically, I want to continue this project. I have another year in the VFP. I want to continue this, and I have many undergraduates like Aaron who are very much interested in this kind of work and research experience. St. Mary's is a Hispanic serving institute, primarily undergraduate institution, many first generation college students. And so we're very, very interested in getting more students involved. And so I'm looking to keep working with this team and with the VFP one more year. All right, I am done. So mine's pretty short. Okay, do I have any questions here? Okay. All right, I see that was my countdown. All right, so I am done.
Anyone have any questions for Richard? You can either put them in the chat or you can say it out loud. Going once, going twice, no questions?
Can I ask you a question, Richard?
Sure. Hi.
For the first slides, you mentioned there's a package, the adaptive refinement time domain. Can you please go back on that? How did you try to use that to your problem before?
The AMR capability, is that what you're talking about? No, so that is not being used. That is so in physics problems, you've got many different scales. And so some sort of adaptive mesh refinement is very, very, very useful. That is definitely something in the future to work on. But right now we're just trying to get it to work for the superconducting material. So we haven't put the bells and whistles on it just yet. Once we get it to work for simple cases, then that's definitely going to be on the docket to work on the AMR capability coming from AMRX. Yes.
Yeah. I think I have seen the applied math department in the lab. I think is that the package from the group there in the lab or from other lab in Livermore?
Oh, this is a package from this lab, from Berkeley Lab. Yeah, this is Artemis. This is being developed by the microelectronics team here.
Okay.
Here at Berkeley. Yeah. In the computational center for science.
Yeah, I've seen that before, but I am not quite related to about to use that package yet. So it's just okay. Yeah. Good to know. Yeah. Nice talk. Thank you, Richard.
Yeah, no problem. Thank you.
Any more questions for Richard? Okay, well, we'll move on to our final presenter of the day, Ms. Vidya Ganapati.
All right, I will just share my screen. All right, can everybody see that? Okay. All right, so I would like to talk a little bit about my work today with my VFP collaborators. And I'm coming from Swarthmore College. And Swarthmore is a small undergraduate institution near Philadelphia. We're slightly smaller than St. Mary's. We have 1,600 undergraduate students. So pretty small, and no graduate programs. And I have 3 students here with me this summer. 2 are VFP students, Min and Ray, who I think might be on here. And Judith is another student not funded by VFP, but is working remotely with us. And we are working with 3 wonderful collaborators from Lawrence Berkeley, Vincent Dumont, who's a postdoc, Talita Persiano, who is affiliated with Advanced Light Source, and Julianne Muller, who is our primary mentor. And so in this presentation, I want to talk a little bit first about some ongoing work in my research group. And then I will talk about how it relates to the work done by Julie and Vincent and Talita, and what we're doing this summer. Okay, so let's get started. So my field of research is computational imaging. So what this means is we design things like microscopes and cameras. But when we design these imaging devices, we don't think of them as cameras in a traditional sense. We think of things like magnetic resonance imaging, MRI, or computed tomography, where instead of just taking a photograph of something, you take many images and you computationally reconstruct them into something like a 3-dimensional reconstruction. In this presentation, I first want to start by talking about a computational imaging modality that we use in my lab at Swarthmore called Fourier ptychographic microscopy, which is very related to the computed tomography work we're doing here at LBNL. Okay, so let's just talk about microscopy for a minute. So there are a lot of trade-offs in microscopy. You can trade off resolution, so the quality of the image, for the field of view, which is how large an area you're imaging. You can also trade off things like cost, and you can trade off additional functionality like getting 3-dimensional imaging or phase imaging. And then finally, you can trade off speed. And that is the main trade-off that computational imaging devices make. They take many images and they get something very high quality or 3-dimensional, but it takes a lot of time to get those all those images. And that's the problem we're focusing on tackling. And so let me make this more concrete. In a microscope, you can use a low magnification objective and you can get a very high field of view. You can see a lot of things, but your resolution is poor. So if you zoom in on this image, it'll be blurry. On the other hand, you can use a high magnification objective. So you can zoom in and you get a very small field of view, so small area, but you get very high resolution. It's very crisp, this image. If you go back to the low magnification objective and you zoomed in, it would look blurry. And so one recent technology, okay, so yeah, so what we want to do is we want to get both high resolution and high field of view. We don't want this trade-off. And this is useful for things like pathology or just biological studies in general. So one recent solution that has emerged in the last decade is something called LED array microscopy. And so this is just one technique of many ways to do this, but it's a really nice technique because what you do is you replace the light source of your microscope by a light emitting diode array. So it's actually like just a toy array you can buy from something like Adafruit, and you can turn each LED on and off individually. And so you can sweep all the LEDs and you can get a stack of images and you can process those images into a very high resolution, high field of view, complex object. So you can get the phase of some specimen. And so phase relates to the refractive index of the specimen. So you can image things that are transparent with this technology. Okay, so that's a little bit of background about that. But the problem is you have to take one image per LED. And these arrays of LEDs can be 256 LEDs, which means that your microscope is 256 times slower than a normal microscope. So If you add the speed axis, you have very low speed. And what we would like to do is we would like to get somewhere here. We have resolution, field of view, and speed. And that's where we turn to some machine learning algorithms. Okay, so I like to show this analogy to make it clear what we're trying to do with machine learning. Say we have a bunch of images of something similar, but not the same. So we have a bunch of images of kittens. And what machine learning can do is that if you have a new image of a kitten that, say you have some camera and this camera has patches of its image sensor missing. And so if you took an image like this image is not included in our original training data set of images, but what machine learning can do is it can learn from a prior data set and try to fill in those gaps. It can try to fill in this image to make it a complete image of a kitten. Okay, so that is not what we're going to do, because the problem with this technique is that you need this training set of kitten images. And that might actually be impossible to get in a biological or scientific setting. So for example, our problem of interest here this summer is imaging at the advanced light source and doing computed tomography. So to do computed tomography, you need to take about 2,000 images of a sample. And you're taking images with X-rays. So a lot of objects can't take that radiation damage and will just deform or get destroyed during measurement. And we're of particular interest, we're looking at bone fragments. So you can't take enough images. There's no way to get these training examples because you cannot take images of any of the samples. So we kind of have a chicken and egg problem with computational imaging. It's very hard to directly apply machine learning because you can't get the training data set. But if you could get the training data set, you could apply machine learning and make computational imaging a lot faster. So our general idea is to say, okay, well, we can't get a training data set, a complete training data set, but we can get a partial training data set. So we can get all these images of, say, kittens, and we have our camera, which magically scrubs out part of our image. But from all these partial examples, our hypothesis is that we can learn enough to complete all these images. And our hypothesis also says that if the region of the image that's missing is different for each of these images, like some of them were missing a segment of their body, some of them were missing a segment of their face. If it's different from all these, we have enough information that we can pool together and figure out how to complete these images. Okay, so in terms of Fourier ptychography or computed tomography, what we say is, okay, well, we can get some of the stack of images that we need, and from that we can infer the rest. All right, so I think I'm running out of time, so I'm not going to go over the math in detail, but essentially, in summary, we use what's known as a variational autoencoder. So this was developed in about 2013 and has seen a lot of success in generating photorealistic objects. So it's used a lot for graphics or just kind of for like artistic purposes. And so what we did is we modified it to include some physics. Okay, so this is a regular variational autoencoder. What we did is we modified it to include the physics of image formation. So we know, if we know what the ground truth object looks like, we know what the measurements should be. And in computational imaging, we try to do the inverse problem. We try to take from the measurements, we try to figure out what the object should be, which is not easy to do. So, but the other problem going from object to measurement is quite easy. And so we modified the variational autoencoder to include that information. And from that, we call it the physics-informed variational autoencoder. And so we did a proof of concept with synthetic data. So these are foam images that you can generate from a Python package. And we said, okay, let's say we have a bunch of objects. We don't have full measurements on any of these objects, but since it's synthetic data, we can validate with ground truth. And so we found that our method could do actually better than standard iterative methods for computational imaging. So what's of interest is to the far left is what we're trying to get. And our method is shown, the image to the right is our method. And the image to the right of that is a conventional iterative algorithm with a lot more data than our method. Okay, so for the iterative solution, we take a stack of 29 images from Fourier tychography. And for our method, we just use a single image, but we have a different single image for every object of our training data set. And we're able to actually reconstruct better. And the larger our data set is, the better we can do. Okay, so it is 2 minutes past 1. So I will summarize quickly. And so what we're doing right now is we're working with this great team. This project is pretty much led by Vincent Dumont. And Vincent has created this package called Hippo, which allows you to do hyperparameter optimization of kind of any optimization algorithm, but in particular machine learning algorithms. And so what we're trying to do is we're trying to make our method more robust, more stable, and more accurate by applying hyperparameter optimization to figure out what's the best design of our neural network and what's the best design of our other hyperparameters such as training rate and steps, training rate and number of iterations and other quantities like that. And I also have, and these are also pictures of my 3 students who are working with us. And and we are still generating results on this particular project, but we have some promising progress so far. Okay, and so to conclude, we have our trade-offs in microscopy. And it might seem like, oh, well, now we can, we've kind of eliminated all our trade-offs, but we should always be clear-eyed about machine learning. And there's no free lunch. We do need more training data now. All right, so just want to acknowledge the source of support for this. And so the major support, of course, is the visiting faculty program. And this is the 2nd year of our participation in the program, and we hope to do another year. So thanks so much. And there's some references, and I can take any questions.
I was
Any
typing.
questions for Vidya?
I have a question for Vidya. Hey, Vidya, it's Andy. So you mentioned you need more training data. So how, that seems like it'd be a real issue for the Hippo hyperparameter optimization. Is that a real sticking point that you can't, I mean, you need more training data to be able to validate this, don't you? So how are you getting around that at the moment?
Like, you mean that because we don't have any ground truth in the real application, how do we validate?
Well, if you have limited training data, isn't there a larger range of uncertainty in the parameters that you're computing? So it's just a matter of quantifying that, and you say, here it is what it is based on what we have. And
exactly. So, okay, so I think there's 2 facets of your question. So first of all, Hippo is great for uncertainty quantification, actually. That's one of the main features that distinguish it from other hyperparameter optimization techniques. And another thing about this method is it attempts to get a posterior probability distribution for every training example in our set. So so what we're hoping to see is that if you don't have enough information, the posterior probability distribution will just have higher entropy. So you'll be able to diagnose problems that way if you have limited training data. And we have limited training data in the sense that no example is complete, but that doesn't mean we're limited in the number of examples. So we could have lots of examples, lots of partial views of many different objects. The limitation is that each object only has a partial view. So that's really the limitation here, not the total number in our training data set.
Got it. Okay.
That makes sense.
Yeah. Thank you.
All right, thank you for the question. Okay, there was a question in the chat.
Can you see it?
Yeah, okay. So could you elaborate on the timescales of your imaging? Is this method agnostic of total scanning time? Okay, yeah. So for timescales, okay, so the particular application here at LBNL is computed tomography. It's actually pretty fast at the, so it's at the beamline, and I don't have the exact number off the top of my head, but it's pretty fast. The images I think are taken at least at gigahertz rate. But we always, the problem here at ALS is not the speed, it's more the X-ray dose. So you want to reduce the X-ray dose. And then the other application for a tachography is kind of a standard microscope. So the frame rate is more like 30 frames per second. All right, so this method is not agnostic of total scanning time. The more time you use for acquisition, the better each partial example will be, and the less heavy lifting that the algorithm has to do. And yeah, so more scanning time is better, but this algorithm can compensate if you're not allowed as much scanning time per object. So the problem is if the object moves or if the object is destroyed during measurement. So instead of taking one object and destroying it in measurement, you take like 100 objects and you reduce the scanning time per object, but it's still better to have more scanning time per object. Does that answer the question?
Thank you. Yes, and you actually pointed to what I was trying to guess. So moving object imaging is possible, but how about a moving object has water in it and it's like a living material?
Yeah, exactly. So that's what we're trying to do. We're trying to, do like living objects. So it's actually, there's a little bit of a subtlety there, is that you basically keep measuring the object as it moves, and you basically have to tell the algorithm how much there's a trade-off between how many frames you're going to use to reconstruct, or how many measurements you're going to use to reconstruct a single frame. And so the more measurements you use to construct a single frame, the better posed the problem is in terms of how well the inverse problem is defined, but then the worse blur you're going to get. So it's actually like, it's a very subtle point, and we're not exactly sure what will happen with the live objects quite yet, because we're still in the realm of synthetic data and or experimental data, but experimental data that's more well defined. So that will be interesting to see.
Thank you.
All right, thank you.
Any other questions? Well, that concludes our speaker series for today. The next meeting will be July 21st at 12 noon, and you can use the same link that you used today for access. Thank you all for joining.